We are talking about Minkowski distance in machine learning. So machine learning is all about clustering of data. Data are placed in clusters. If they are not placed in well clusters, then we use various algorithms to distribute it in clusters. So data has to be in clusters. Now if I have a test data, means trained data has to be in clusters. If I have a test data, then test data, it should belong to a cluster. How it would go and map to a particular cluster, one of them. That is the kind of the idea of machine learning. There are many ways where we can kind of map the test data to a particular cluster, kind of neural network or Bayes theorem, NLP, or decision tree. There are so many. One of the basic way to place a trained test data to a particular cluster is finding the nearest cluster from the test data. If I have a test data, then all clusters in the test data, they have a distance. So if we are talking about strings, then Levenstein distance that comes into the picture, where it talks about the distance between two strings. So if I have a string A and B, what would be its distance? So if I calculate the distance of a test string with all the trained string, the nearest would be where it would go. So that is Levenstein distance. There is another distance called Minkowski distance. Minkowski distance is about numeric value rather than string. It's about numeric value. So if I have a trained data of single dimension, 2-dimensional, 3-dimensional, 4-dimensional, or n-dimensional. So 2-dimensional, single dimensional means it is on a particular axis, x-axis or y-axis. 2-dimensional means it is on xy plane. 3-dimensional means it is on xyz plane, like if it grows in the dimension. So Minkowski distance is a kind of a distance between 2 points that we can calculate, and these 2 points, the distance what we get, upon this distance we can now estimate that this test data belongs to which cluster. So we have set of clusters and we keep on calculating the distances, nearest cluster where this test data belongs. So that is Minkowski distance. Under Minkowski distance, two distance comes into the picture. One is Manhattan distance, one is Euclidean distance. So Euclidean distance is, I think, it's well known. If I have a 2-dimensional data, that is x and y, and means one is x, that is x1 and x2, and other is y, that is y1 and y2, then distance would be a subtraction of each dimension, and then we have to place a root over their squares. So that is Euclidean distance. There is a Manhattan distance, where it's a kind of, it is called like a taxi distance, where we go in one direction, we end up, and then we move in another direction in 90 degrees. So if I have to find a distance between kind of 2, 2 and 4, 4, then we will move along x-axis 2 to 4, then we will move along y-axis 2 to 4. So this is Manhattan distance. Euclidean distance is a kind of diagonal. So if 2 points are there, and if I make 2 points as 2 end of a rectangle, then it would be the diagonal distance. So these two are the distances that comes into the picture, Euclidean and Manhattan. If we combine both, kind of a union of these two distances, then it comes to Minkowski distance. So Minkowski distance is to find a a kind of a cluster where a test data belongs to, and this decision of finding the process of finding the exact cluster is the distance between the test data and the cluster points. So through Minkowski distance, if data is n-dimensional, like we talked about right now, two-dimensional x and y, it can be x, y, z, and so many. So that we'll see that how we can calculate the distance between 2 points in Minkowski distance. And then followed by we'll place an example where like if I have a RGB image, then RGB means it comes to 3 dimension. So how two images, how far they are from one image to another image, and how we can kind of calculate the distance, and how we can kind of we can map one image to other through Minkowski distance. So that as an example that we see. Further the discussion on Minkowski distance. So we'll see the slides and example. This is Linux. So we'll go find website. So Minkowski distance, like it is to find the distance between two coordinates. Coordinate can be multi-dimensional. Different algorithms are used at each dimension. Okay, so it's a kind of combination of two algorithms, two distances, used mainly for numeric value. It's not like a Levenstein distance where it is used for find the distance between two strings. Minkowski distance, like if there are two buildings, then there are distance between it. If there are two strings, there are distance between it through Levenstein distance. If there are two coordinates, here it is of 4 dimension 4, then what would be distance between these two? If there are two strings, distance can be found out by Levenstein distance. If there are two entities, two kind of coordinates with here it is 4-dimensional, what would be distance between two? So here Minkowski distance comes into the picture. Okay, so first we'll talk about Manhattan distance. If there is a point x, there is a point y, then distance has to be in x direction. We have to move till we reach here, and then in y direction, or we can go like a staircase like this. So this distance, red one and plus green one, this distance. If we add these two distances, it becomes Manhattan distance. So if I have n coordinate points, then first one minus first one of the second coordinate, first point 1 first coordinate, point 2 first coordinate. If I subtract and then keep adding and go up till the last coordinate in the point, that becomes Manhattan distance. So in graphics also, like this is 2-dimensional, x to y, and if x and y are 3-dimensional, if it is alpha 1, beta 1 and gamma 1, and then another point has coordinate alpha 2, beta 2 and gamma 2. First, it moves along the one axis, then another axis, and then on another axis. So, it could be like along x-axis, y-axis, and then z-axis. So, distance between x and y would be alpha 2 minus alpha 1 plus beta 2 minus beta 1 plus gamma 2 minus gamma 1. So, that is Manhattan distance. Let's talk about Euclidean distance. This is another kind of distance where if I have 2 points x and y, then the distance between x and y is alpha 2 minus alpha 1, beta 2 minus beta 1, gamma 2 minus gamma 1. Then we have to square it and then a square root of all the addition. So that comes to Euclidean distance. In the 3D graphics, it would be like that. If there are 2 points x and y, then this is the distance, red cube. So that is supposed to be the shortest distance between these 2 points. So we talked about Manhattan distance. That is a kind of axis distance. We move along axes and find the distance. Whereas in Euclidean distance, we try to get direct distance. What is Minkowski? So, if we see the formula, then it is xi minus yi, that is Manhattan distance. Xi minus yi square, then a square root. Here, if I say instead of 2, it is 1, and instead of 1 by 2, it is 1 by 1. So, Euclidean distance becomes Manhattan distance. So, we would generalize it to a p, x minus y power p, and then to the power 1 by p. This becomes Minkowski distance. So, this is Minkowski distance. If I have 2 points x and y of n dimension, then for each dimension we subtract raised to the power p, then we add it, and then we calculate 1 to the power p. That comes to Minkowski. It can be kind of a superset of Euclidean distance and Manhattan distance. Okay, so in RGB, in image world where we have 3 coordinates mainly, if I exclude alpha, then for every pixel has RG, R1, RG and B, red, green, blue. So if I need to find distance between 2 pixels in an image, that distance would be D. So as per the Minkowski distance, so if I follow Euclidean distance, then it would become R1, R2 minus R1 square, and G2 minus G1 square, B2 minus B1 square, and the square root. So that would be the Minkowski distance if I consider the power 2 between the 2 pixels. Okay, so let's proceed in the Minkowski distance. Okay, so I have a point called which has coordinate alpha, beta and gamma 1, and I have a point which has distance alpha 2, beta 2 and gamma 2. The Euclidean distance or Minkowski distance between these two is capital D. If I am at distance x and it has a coordinate ABC, it has a coordinate value ABC, what would be ABC? Okay, so it's not that difficult. It would be alpha 2 minus alpha 1 and then divided by the distance into x plus alpha 1, similar to beta 1 and similar to beta and gamma. Okay, so what we want to achieve here is that given a distance d, and then for variable x, where x is here, and it will vary along the line. So it will vary along the line. And what would be the coordinate ABC? Okay, so there is a mathematics and we come to same simple conclusion, like x would be a minus alpha 1 and beta b minus beta 1 and c minus gamma 1 to the whole square, and slowly we will come to a calculation, and if we differentiate through d alpha. Okay, so on the right side we'll go with simple mathematics of differentiation, and slowly we'll come to the same result what we were talking about. A minus alpha 1 equal to x into alpha 2 by alpha 1 divided by d, and then it comes to a equal to x into alpha 2 minus alpha 1 divided by the capital D, where is that is the Euclidean distance between these two, and then the alpha 1. So if I know alpha, beta and gamma, that is the begin point. If I know the distance d, and if I know the end point alpha 2, beta 2 and gamma 2, for any distance x, the coordinate of ABC would be this. Okay, so Minkowski distance will prove it. Like if I have an image, two images of equal width and length, then every pixel between two pixel of the images, like I have two images, one image is this and another image is this. Every pixel has RGB, that comes to three triple dimension. Two coordinates are there, and every pixel, between every two pixel there is a distance. So if I okay, so between every two pixel there is a distance. So idea is that if I can able to calculate the Minkowski distance, then through this formula can we transition and one image to another image, so that we feel that Minkowski distance works. Like example image we have taken, like I have a kind of face of a cat, and then this is source image and this is the target image. Now every pixel between this tiger and the cat, we know the distance, we know the maximum distance. So what we would do is, so we know the d, that would be kind of maximum distance between all the pixels, and then for every pixel we now, if we know maximum distance, then pixel by pixel we can proceed x, like x can be 1, 2, 3, 4, or I can say 1, then next time 2, next time 3, next time 4. Based upon the varying x, we would calculate ABC, new ABC, And so if I have new ABC, then I will have a new image. So for every pixel, we will calculate a distance from the pixel. For that distance, we will calculate a new RGB, and that RGB we will draw. So this is the first image, this is the second image, this is the third image. So slowly image is kind of proceeding from the source to target. Like if I have alpha, beta and gamma, and then I have to reach alpha 2, beta 2, gamma, then x we can start from 1, proceed to 1, 2, 3, 4, 5, 6 till it reaches alpha, beta, gamma. That is the distance d. And keep on calculating ABC, and then for each pixel we draw the ABC. And slowly we will see that since the pixel value is approaching towards alpha 2, beta 2, gamma 2, that is alpha 2, beta 2, gamma 2 here. From alpha 1, beta 1, gamma 1 here. Then slowly we will move towards the other image. That is the idea. So we can see that cat image is slowly coming to a transition, and then it becomes the target image. Okay, so we'll proceed for the coding part. So we'll see that how we can calculate the Minkowski distance, and then how we can calculate the Minkowski distance, and then how we can transition an image from source to target. So we'll use a Python package Kivy, because we now need a kind of texturing, splitting the texture from image data. So we need OpenGL for this concept. So OpenGL through Python, it works well in Kivy package. So we'll use Kivy and we'll see. Okay. So we will proceed now for the writing the code. So we'll use Kivy as per the we stated that we would use Kivy. We'll create a directory called Minkowski Distance. Okay, so directory is empty. We will create a file called md.py, Minkowski Distance.py, or Minkowski Distance image transition. So we will use a 2.1.0 version of the Kivy that is installed here. From Kivy UIX widget. Import widget. Kivy dot app, import app. From Kivy dot graphics, here OpenGL comes into the picture. Import rectangle. Okay, so for image manipulation, we use PIL, PILO library. So from PIL, import image. That is the idea. Okay, now from scpy dot spatial, we would import Minkowski distance. We'll have a global function depth, and that would give us kind of a difference in the among the images, kind of depth. Image 1 and image 2. So if I pass these two images, it would provide the difference. Image 1 buffer equal to image dot open image 1, and would fit the bytes in that. So image is opened in RGB and it is converted to byte. We'll have a variable I, and that is equal to max distance, and that is 0. So just initialization. And now we can say I less than length any of the image box, because we are taking equal length image. So till it is less than image box, we will say max distance equal to max Minkowski distance. Okay, so okay, now Minkowski distance, if you see the signature, it takes two arrays of coordinate. So this is the first array of the coordinate. This is the first array of the coordinate, image 1 buff I to I3, that is the first 3 pixels, that is RGB. So similar way, we will create another array now. Int x for x in image 2 buff I to I plus 3. and for the coordinate 2 and the max distance. Okay, so this is the code. So max, whatever Minkowski distance we are calculating, this is the first array. Int x for x in image buffer I to I plus 3. Second array, int x for x in image 2 buffer I to I plus 3. And then third parameter is power 2. Okay. Okay, so we are taking power 2. So P, that is Minkowski distance, P is 2. Now we would make I plus 3. That's it. And we would return now image 1 buff. We can print it actually. What is the maximum distance between Minkowski distance? What we have calculated pixel by pixel. So we are calculating pixel by pixel. Each pixel we are calculating the distance and maximum distance we are returning. Oh, sorry. So we will print max distance between images. That would be max distance, and we will return the buffers now. Image 1, buff, and max distance. Okay, so our D is calculated. In this calculation, D is done. Maximum distance. Now we will have a pointer x, and that would increase from 1 or whatsoever, and we would keep calculating ABC, the coordinates, and then we'll draw the image, whatever we. Okay, so we'll have a class now. I can say my widget, and that derives from widget. Def init. So it is kind of a constructor. We'll have variable. We'll call parent first, super my widget self. Self dot distance max equal to 0. Now we would call this function self dot image 1, self dot image 2, self dot max distance equal to, so global function what we have written now, that function okay. So we have received image 1, image 2 and the max distance. We will have self dot rect equal to none, and now OpenGL part we will have a canvas with self dot canvas and self dot rect equal to rectangle argv. Okay, so with self dot canvas self rect equal to rectangle, we are drawing a rectangle, and that rectangle we would play with, in the sense we will provide texturing into the rectangle and we would update the texturing. That is the idea. Okay, so we'll catch the signal on size and here we would complete self dot rect dot size equal to, so this is a tuple self dot width self dot height min self dot width height. Okay, so this is what the size is, and position would be at the center, self dot center x minus self dot rect dot size center y minus self dot rect dot size 1 by 2. Okay, so first one is self dot center x minus self rect size. So idea is it should be at the center. Now we have the app class, that is my widget app derived from app, and def build self return my widget. If name equal to main my widget app okay, so this is the code, only one file we have. Now we have Kivy imported widget app rectangle from PIL import imported and SCPI special import Minkowski distance. Now in the diff we open the two images and we calculate I equal to I plus 3, means for every pixel we calculate the Minkowski distance between these two images and we get the maximum of the maximum distance. So at the end we get the maximum distance that we print, and then we have my widget that derives from the widget Kivy widget Now we call super. We initialize the super widget. Okay, distance index 0. We call the function what we wrote now. Sysarg1 want these two images we would push in when we call the function, and image 1, image 2 and max distance that it returns. Okay, rectangle we initialize source equal to sysargv1. So that is the source of the rectangle, and rectangle width, height, so size and pause we initialize. We can run this program kind of. I can copy one image. I have image of the cat. So I have two files now. I can say Python Python 3 cat.png. Okay, it takes two arguments to calculate the distance. So probably I can copy another image also. That is of the tiger. md edit cat.png and tiger. Okay. Okay, sys is not defined. We'll import sys also. Okay, module sys has no attribute. Okay, so it draws the image that we can see pretty well. So image has come. Now idea is that we proceed on transitioning the image through Minkowski distance. So we would write that code. So okay, so here we are. Now I can add that definition. Def. So we would catch touchdown on touchdown. So self.index we had initialized to 0. Now this index would proceed. So I can say min self distance index plus whatever touch is. If touch is touch button equal to right, touch button equal to left, and 20. So if it is left, it would proceed 20, or if not left, then maximum of 0 and minus 20. It should not go below 0. That is the idea. Self.max distance. Okay, so this is the code. Distance index we are increasing. For every mouse press, distance index would increase by 20, or it would decrease by minus 20 if it is a right mouse button click. And then self max distance, whatever is minimum. So in the sense that it should go maximum up to maximum distance. Maximum distance what we received through this. maximum distance and distance index. So maximum distance is distance between two images. Maximum distance is distance between two images, that is D capital, that we calculated. And now we are increasing the distance index. Distance index is x. So this x would start from 0 or 1 from so it would start from here and slowly it would proceed along the Minkowski distance. So now it starts from 0. It starts from 0 and with every mouse click it would proceed with 2020. Okay. Now we would split it. So we can print what is the distance index right now. We can say self dot distance index equal to, that's it. Now we would go with our work and we will see self dot rect, that rectangle. There the texture, what it belongs, we would split the texture. So self rectangle texture, we would split the buffer. Bytes. So this would be long expression and it will be as per the calculation self dot image 1 count plus self dot image 2 count minus int self dot image 1 count self dot distance self dot max distance for x in range in plain self dot image 1 by 3 for count in range x into 3 x into 3 plus 3 plus 3 Breathing format is RGB and that's it. Okay, so this is what we have written. First is self image 1 count. So we are iterating. What we are doing is for x in range int length. So whatever is the length of the image by 3 means every pixel. Every pixel has 3 component RGB. So if I divide by 3, it would come to the number of pixels. So that we are getting. And we are iterating pixel, then we are for x in iterating pixel by pixel. For every pixel, now we are iterating the RGB. So x into 3. If x is 0, it is 0 into 3 plus 3. If it is 1, it is 3, 3 plus 3. So 3, 4, 5. Okay. So the value, so count is RGB. So image 1 R, image 1 R, if I take R, image 1 R plus image 2 R minus image 1 R multiplied by distance index x and then divided by max distance. Okay. For whole stuff, whatever we receive, we convert into int. So we get a kind of a buffer, int buffer of the ABC. So this formula, now we convert it to bytes, and then in the buffer we pass another variable, color format, that is equal to RGB. So now we'll start again. First is image 1 count. So first image 1 RGB we are calculating. So here we are. So we are trying to achieve ABC, that is RGB, and alpha, beta and gamma. Whatever is alpha, that is this one, plus alpha 2 minus alpha 1 plus alpha 2 minus alpha 1 multiplied by x, that is the variable distance, multiplied by distance index. Okay. And whole we divide by max distance. Okay. And whole we divide by the capital D, the full expression. This is common among all these, and that is nothing but the capital D. Okay. Now whole we convert it to int, and it becomes a list in Python terms, and list is finally converted to bytes, and that bytes is fed into the texture. Color format is RGB. That is the idea. So we proceed. Okay. So we are here. We are here. Now we proceed with the editing the code. So we have blitted the buffer, and now we will say canvas for update. Now we are forcing for its shaders to update the texture. Super my widget dot self comma self on touchdown That's it. It's a small program. Now we have diff. We call diff. We call diff and get the image 1 buffer, image 2 buffer, and then max distance. Okay, and we remember this as a instance variable. We have a rectangle, and with every touch down, we check if it is a right or left. Left button we proceed with the 20, and right button we come back to 20. Okay, and we split the buffer every time with the distance index, varying distance index, and then we calculate the new RGB for the buffer. Okay, and we split the buffer. Okay, so first we iterate pixel by pixel, followed by we iterate every pixel x into 3 and x into 3 plus 3, and then we update the canvas, ask for ask update. Sorry. So self canvas dot ask update, super my widget self on touch down. Okay, so we'll try actually. Now we have cat and tiger. I would call this function mdedit cat.png tiger. Okay, so pixel by pixel it should proceed. That is the idea. Okay, so I'll press the mouse. Okay, so self index is growing. It is visible. It is 40 now. Okay, so we can see it's changing. Now we can see the essence of tiger. If I go back, okay, so I can right click. Okay, so I have mouse with me now. So I can right click and we can see if it is going back. Self dot max index should go back. Okay, so right click is drawing drops. So this is multi-touch machine screen. It is behaving like what we can do is, so I have a file. disable multi-touch. So disable multi-touch is nothing but it would just in the configuration it would disable the multi-touch. So we can import this in our file. Import disable multi-touch. Disable multi-touch. Disable multi-touch. Multi-touch. We'll try again. Okay. Now I am pressing left button and index should proceed and we should see the changes. Okay. No changes. Okay. Now it made a change. Okay. So change is visible. Okay. Now pixel is changing. New pixel values are coming and it is approaching toward the tiger. Okay. Okay. So tiger image is more visible now. We have reached distance to 80. We'll see what was the maximum distance that we have printed somewhere. Max distance is 480. Between every pixel, if I calculate the distance between every pixel of two images, maximum comes to 480. So it would go up to 480. We are at 280, but still tiger images can be seen. It is more prominent. We'll see if our right click works. No. Oh, it doesn't work. It should go back. Distance index. Okay, set distance index. Minimum touch button equal to left and 20. So it will return 20 if it is left, or maximum of minus 20 or 20. Okay, so it is returning 0 for the right. If I make minimum of 0 and minus 20, then it would return minus 20. Okay, I think we can remove this fancy and we'll return minus 20 plain. So left button is, then it is 20. If it is right button, it is minus 20. So it should decrease now with the right button. It should not go beyond 0. That is the idea. So probably we can make here in min max, we can make one more. Okay, so kind of max 0 and that. So it should not go below minus 20. Try again. Okay, so I'll press left mouse and it is growing. We can see 20. Now distance is 20. Distance is 40. So cat pixels are changing now. So now it is a hybrid image. I'll press right button. It should go back. It's going back. It is a kind of it's a hybrid image, and so if I go back again, okay, someone can say this is a cat. Now if I proceed, okay, so now we are at distance 120. So at 120, this is a kind of hybrid image. No one can say it is a cat or tiger. Okay. Okay. We are at distance 240, 260, 280. Okay. At 320, it is a kind of, but see here the pixels. Cat ears can be seen. So it is not fully converted to tiger. So it would go beyond that. Okay. So that is the last. 418 is the last. Now there should not be any presence of cat. There is nothing. It's a pure tiger now. If I press right button, it should come back. It is coming back. 398, 378, 358, and it is decreasing. Okay, so it came back to cat from the tiger. So that is the idea. I have another image also for smooth transitioning. So what we have done is we have incremented 2020. That is not fair, and it should be 1. So it would be smooth. So that is the goal. Okay, anyway, I have another image that we can just see. So we'll call again and Newton and Einstein. Okay. So prior to that, I think better if we print the maximum distance also, kind of. Here we are printing self distance divided by self dot max distance. You can use FR. Okay, so it would be more informative. Okay, self distance is 20, where max distance is 404. So up to that much it would go. So we'll try now. 20, 40, 80, 100. So photograph is changing. 120, 140, 160, 160 by 404. But I think it's visible. Okay, so Einstein is visible now. We are at distance 280 out of 404. Okay, so once we reach 404, it should be completely converted. Yes. We reach the maximum and it is completely converted. We'd go back with the right click. Going back. Okay, still it is Einstein and we are at distance of 244. Now it is more towards Newton. 164. So we are at distance 104. If we come to 0, it is all about Newton. So that is it. And then, as we talked that we can make it smooth, it is not smooth. It is 20. So we can have a clock. We should iterate every second and it would save in a file. What we can do now is from Kivy clock import clock and we'd start a timer. So in the constructor itself we can start a timer here, that is clock dot schedule interval self dot update GLSL. So we'll give a function name update GLSL. Every half second we will call this schedule clock dot schedule interval and self update GLSL and 1 by 2. Okay, we can comment this, we don't need this. And here instead we will have update GLSL. This is the grammar for the clock callback function update GLSL self delta, and we don't want this also right now. And we would save this. Now this would convert to 1. So touchdown, everything gone away, and we would just increment y self index. Every time it comes, it would increment it by 1, or self index equal to max self dot distance index plus 1, or self dot max distance. So it would start incrementing by 1 and it would go up to the max distance. Okay, that's it. Is the change required? Now we would save this in a file. Okay, so we can say self dot rect dot texture dot save. Now we'll save this texture into a file. I can say cat tiger plus str will have one counter. Z fill with 3. Now we have a string counter and Z fill 3 plus dot png. Flip equal to false. OpenGL and PNG grammar is different when y-axis comes into the picture, and we do it if self dot distance index not equal to self dot max distance, else we don't do it. Now we'll have another guy called in self dot counter equal to 0. And every time it enters, counter grows. Self dot counter plus equal to 1. So initialized to 0 and then incremented by 1. And then we do rect texture save cat tiger plus number, a number of the image, Z fill by 3, so it is 3-digit number, and PNG flip equal to false, not equal to max distance, else none. So we can continue. These are the files right now. So I'll run the program. Okay, so it starts with Mr. Tiger. This is not what we want. It is doing something else. Byte must be in the range 256. Okay, self distance index plus 1, max, so it is going there only directly. It should be min. Okay, so distance, and if it reaches max distance, it would stick to max distance. That is the idea. Okay, so counter is working, timer is working. 1, 2, 3, 4. So it would do smooth transitioning from cat to tiger. It would take some time because bleating takes time. It is not that quick. So slowly it would move from cat to tiger. Now it is moving one by one. So X is moving 1. Earlier we were moving 20, 20, 20. Now it is moving 1. Okay. So now it is at distance 26. Probably we can check if files are being generated. Okay, so files are coming. That can be seen. It is at distance 49. We'll watch till Tiger Essence starts. Okay, so it is distance 62. Tiger Essence is coming. Okay, so it has reached till state 89 by 418. So certainly change is visible. Okay, it is more visible. Okay, so Tiger Essence is perfectly visible. So we have reached to a stage where it is hybrid image. The way we described, like it is going in this direction, and we are somewhere here at the third distance. Slowly it would proceed towards fourth image. It is proceeding. One 45. So idea is that we'll have a lot of images that have a smooth transitioning, and then finally we'll club together all the images and we can create a kind of a video or GIF image that will be quite smooth. So it would take some time because there are a lot. Okay, so we are not much far. So we are at 365. Very slight ear hairs are visible of the cat. So that should go away, and in return it would generate the images what we want. We can browse through the images. Minkowski we have created. Now we have lot of images. Cat, tiger. Every stage we have images generated and it is being saved. You can see the transition. See this funny image. So kind of in between. Okay, so what is the status now? I think it is kind of complete. 418. Now that ear essence is kind of completely gone. Very little is there. Now it is full-fledged tiger. Okay, so we are near to done. Then we would convert it to a video and then we can see it more smoothly. Okay, so it is over. So both are at same index. So it is done. So we reached from cat to tiger. I can just close it down. And I have lot of images. I can just say FFmpeg minus frame rate some 40, 10-second image will generate. And in my I'll say cat tiger and percent 03d.png and output would be cat minus y cat tiger Minkowski Distance.mp4. Okay, so FFmpeg is generating what we want. It is done. So we have this file now. I can see this file. Cat tiger. So I'll double. Okay, so it would bring a video. Now smooth transitioning can be seen. How it happens. Pixel by pixel. If you are looking for Kivy or machine learning trend, or you are looking for Kivy and machine learning application development, or you are looking for porting your QTQML application to Kivy, or you're looking for 3D OpenGL application development, you can contact us. You can also sponsor our videos. Please do contact us.